All right, so we're back. Remember, our goal today is to train. Actually, training shouldn't take that long to do. Okay. Um, right. So we're just, we've covered a lot from the beginning, the guys. All right. So guys over there. So we've started with our text. We've converted it to IDs, and we are now going through the logic of the first class, the GPT, and that starts to build everything else, right? So I'm going to start then in forward now. In the previous lecture, I covered the init function, and that has been defined now. So now we're going to go ahead and define forward, right? So key things to know. Forward works both, guys. So forward works both for training and for inference. Okay. So during training, we need X and Y, right? We need those two shifted tensors to train. During inference, like let's say you're talking to Chat GPT, you're no longer training, right? So you don't need the Y. You just give it the input and Chat GPT will give you the predicted output, right? So that's why in this forward, you will see that there's these two variables, IDX and targets. But you can see that targets is none by default. So if you don't pass anything to it, it probably means you're in inference mode. If you do pass something to it, you're going to be in training mode. But that's essentially the X tensor and the Y tensor, okay? So in this case, the X tensor is called IDX. Just that's the name. Could have a better name. All right. Then notice I just extract the shapes. I like to I live by the shapes, right? So I need to visualize these things. So this is 64 by 40, pretty much. Now, you guys, this is exactly what I did before in previous lectures. So just go back to those on positional encoding. And if you don't understand, because, that was the point of that, so I can not spend too much time here, right? But all I'm doing, if you notice, is I give it the IDX, it goes through the positional embedding, and I get token embedding. The way to think about this smartly is to say, N by 40 goes in, N by 40 by 512 comes out. Do you see that? That's really the key. Then over here, if you guys remember, we did the same thing for positional embeddings, positional encoding. But remember, I gave you this thing that I was so confused, right? How is it that we don't run X through this? And it took me some time to get that little trick that we discussed in the previous one, that it maps the position from 0, 1, 2, 3, 4, 5 to 40 to embeddings, right? But the way to understand this one as well is this goes in, which is that sequence, and what comes out is N by 40 by 512. So now we have the two tensors, positional encoding and semantic encoding, and you add them. This might seem surprising to you that this somehow works, but this is actually a trick used extensively with residuals and things like that in deep learning. It's actually very powerful. All right. And once that's done, this was the baby GPT. And if you remember, from here, we would just go directly to the attention mechanism, right? And we did that whole KQV stuff. We can't do that here directly right now because we no longer have just one block. We have 6 blocks. So that's the next part. So I need to create the 6 blocks, okay? So I need to discuss what blocks is. I'll do that in a second, but let's just finish this code section so that we don't have to come back to it. All right, so assume N by 40 by 12 goes in, and guess what comes out of here? N by 40 by 512. And that is the elegance of GPTs, right? Regardless of this massive complication, you just know what these tensors are going to look like. So then what do? We have this LNF, which, as I said, is a normalization. It happens everywhere, right, for all the values. And then the last thing, LMFFW, is this part here, where we map to the vocabulary. And this was also in the baby GPT. So if you look, all we do is run this tensor X into here, and we produce logits. We've talked about this term logits, right? So it's whenever we have a thing that's approximating like a probability distribution, we call it this term called logits, but it's the result. And this is a tensor of n by 40 by 88 vocabulary size. Got it? Do you guys understand? And this has been covered already. We defined it up here as ln FFW forward. Remember that nn.linear we've discussed already is what we were when we created W and B, and then we took X matrix multiplication W plus B and got a result. NN linear is an encapsulation of all that code into one thing. But it's the fundamental, whether it's called a transformer, a CNN, or whatever you want to call it, this is the fundamental operation. There will be a few others like convolutions are another thing, but we'll learn that later in the semester. So but there aren't that many like these primitive or first principles or whatever operations. Okay? All right. So yeah, if you notice, we've done this. I will come back to this part here when we're training, but essentially once I have my logits, which is my predicted tensor, what do? I compare it with my real tensor. What's my real tensor? Targets. So essentially, targets is n by 40 by 512, or sorry, n by 40 by n by 40. So it's n by 40, and this is n by 40 because it has been mapped back to the actual ID. Right? Yes? Okay. All right, great. So once we do that, we notice over here what's happening is we compare, we have logits and we have targets, and then we're just going to run both of these through something called a cross entropy. And that is the way that we calculate the error. We'll discuss cross entropy also in the second third of the semester, but for now, just that's the place where we take the predicted and the real and see how different they are, and we use that information to back propagate, okay? That's a topic that this, a simpler problem is better than this to understand. But it's the same cross entropy. There's only cross entropy and MSE for optimization, essentially. Okay? All right. So anyway, that's the optimization part. We'll come back to this, so don't worry so much about it. All right, so now let's focus on architecture so that we can wrap this up, right? So I said after token embedding is added with positional embedding and we have X, we run it through this thing called blocks, this construct, okay? Now, one other observation you should make. If you notice in the way that I'm coding this, I run IDX through something and produce token embedding. Then token embedding is added with something to produce X. Then that X goes into blocks to produce this X. Then this X goes into this one, and that one goes into that one, and so on. Do you see how that works? That is only one of two approaches to code a deep neural network, okay? So there is another approach, which is actually the way that blocks is implemented. So blocks is implemented using something here, this construct called NN sequential. Okay? So this is something, again, that it's more of a programming thing, but it's important. We have two options, and they both work the same, but they have their advantages and disadvantages. And NN sequential can be more convenient sometimes. So I'll show you what I mean. Let's go to the whiteboard because this is an important concept. And we will use NN sequential, for instance, with C. I like using it there because the other approach is just too complicated or too long. So what do I mean? So in PyTorch, there's two ways of building a neural network. The way that I've been doing it, right? So I do linear 1. X goes in and produces, I'm going to use different variables just to indicate, produces hidden 1. Then I use linear 2, takes in H1 and produces H2. Do you guys see that? Then I do linear 3, takes in H2 and produces H3. And I can keep doing this for a very, and I actually really like this approach. But this only works when you have very small neural networks, when you have smaller architectures. If I have 6 blocks, that, and things like that, it gets a little bit more complex. So in that situation, sometimes I can use NN sequential. And then sequential just works like this. So notice here, there's still an X, right, that comes in, and there's obviously the same X coming in. I'm doing the exact same architecture, but just with 2 different approaches. So I can just do and they're the same. Do you guys understand? So I don't have to like explicitly enter that X and have it go through. It is just assumed that if I put these in sequence, X will go, through them in this way, just the same as it will go through them in this way. Got it? Yeah, go ahead, please. Yep. When I don't feel like putting a lot of code in something. No, it's true. Like you could, in theory, build all those, but it's going to be a lot of lines of code. It's harder to debug. It's harder to. So instead of me writing, so right now I need to write 6 blocks, right? Block 1 and then block 2 and block 3. So how am I going to do that? Or I just conveniently use NN sequential and more simply write what I wrote here, but in this way. I do have fewer variables and things like that. Yeah, good. I actually prefer the other method, but see, different people think differently. So I may be one of those people that just likes to like explicitly see exhaustively, every little detail. And that's what makes me happy. But you may just say, I understand that. You can just picture it in your head. So then this other approach is what makes more sense to you. One is not supposed to be more efficient than the other or anything like that. Preference, yes. There's 2 ways of doing it. That's what I was saying. So I can imagine there's some people that write everything with NN sequential, and others want to, as much as possible, like me, to do it this way. It might be because I learned TensorFlow 1, and TensorFlow 1 was a bit more like this. So I just became like, I'm trying to maintain that knowledge, possibly. I don't know. But it's a good question. Got it? All right, great. That's important because we're about to make a huge leap, right? So understand this difference, okay? And now let's take a look at this leap that we're going to make so those 3 lines of code, I had never seen code like that. I had seen it in CNNs, but I had never seen it like in this context. So I was very impressed by this solution. Imagine our architecture is this. 6 blocks, these decoder layers, there's 6 of them. Remember that those decoder layers, if you read through this, hopefully, look like that, right? So N40 by 512 comes in, there's a multi-head attention layer, and that goes into a fully connected layer to come out as an N40 by 512. And that's 1 block, and then there's 6 of these, okay? So we can assume that code will just run through it all, okay? But we create this object called block, and then block is going to be defined in another class, and then that class uses other classes. So think of all the code involved there. So NN sequential here is useful. So pardon? Yeah. But it's obvious, right? You agree. Yeah. So no, thank you. So here we have now, I create an object called self blocks, and I'm using the construct NN sequential, right? I'm using NN sequential. That's the same. Now, what I plug in is a list. You can see that here, right? square brackets, and it's a Python list. This is not even a, but it's pointing, right? It's pointing to the space in memory. That's what that little asterisk is doing. So notice that this is a list comprehension that very cleverly creates a sequence of blocks. Do you see that? How do we do that? You remember that underscore, just whenever you're iterating and you don't want a variable, you just throw it away. So we put in an underscore, right? So we do for blah in range n layer. What was n layer? 6. 6 layers. Okay. Okay, perfect. And then what do? In this list, we create, so we go 0 to 6, right? So we go block, 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 6. We're putting them in memory because that's what the list is doing. In RAM somewhere, block, 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 block. And then we can just grab that whole chunk of memory and feed it to the network. But it's in order. So then when the data comes in, it goes through all 6. Do you guys understand? Right. So no questions? All right, perfect. So you can see that. So we instantiate, this is just a call to the class block. So we're instantiating that class 6 times. If you wanted 12 layers, you can have 12 layers, no problem. You see that? It's a deeper model. But and by the way, everything that I'm using, I didn't just like randomly pick. This is from the 2017 paper, the Vaswani paper. These are 8 heads, 6 layers. So this is consistent if you're reading that paper. Now, what do we provide to block? Notice n embedding is 512, right? So we know what that is by now. And n head is 8. The number of heads, because every block will have to have these 8 parallel attention heads, which we've discussed in a previous class, which you guys should know what that means by now. Got it? All right. So we're done with the class GPT. So the obvious thing to look at now is to define the, what do we need? So these are already defined. Blocks. So essentially block, right? Blocks. For what purpose would you want to access them independently? I guess you could if you want. If you can access them from blocks, like if you called self.blocks3, you could get access to that head, yes. You instantiate 6 equal blocks in a list in memory. We have to define what block is, right? But what I'm saying is NN sequential is the magic. That because you laid out this block and this block, just like I did linear 1, linear 2, linear 3, X will run through them even though I'm not passing from one to the other because of NN sequential. That's the whole trick. Okay. Otherwise, if I didn't use NN sequential, then I would need X goes into block 1, something comes out to go into block 2, comes out to block 3, right? And I'm not doing that. You could do that. Might be a nice, fun thing to do on a weekend, right? Saturday night. Right? Anyway, so we've done this part, right? So this is complete. So now what we need to look at probably is the actual block class, right? And some of these other ones, but they get simpler, right? So let's take a look. So block is the next one. So let's take a look at. We can now think of these independently also because we know what's happening here, right? So block is a decoder layer. Block is a decoder layer. So one of these boxes, any one of them at any time. So we need to think about what's going on here. So 512 comes in and also n heads, the number of heads. Remember, did I think I didn't copy the whole thing. Yeah, sorry. Okay, better. Remember, I'm following that same recipe that I told you about, class, some name, NN dot module, the class inheritance. This is an init and a forward. You see that? In the init, we declare the variables, and in forward, we actually put together the architecture. So if you notice overhead, over here, head size, I'm just calculating that 512 divided by 8 is going to be 64. We've talked about this, right? That's going to be relevant because we are going to perform the KQV. And if you remember, we compress that from 512 to 64. We do 8 heads, concatenate them, and that way we get 512 again. We've talked about this. All right. Multi-head attention. This is another class that we have to define. As the name implies, this is where we're going to do the 8 heads and concatenate them together. Okay, so we will do that we define that as SA multi-head, where we say that the N head is 8 and the head size is 64. That's a calculated value. Once we do that, what did we do? That whole thing will encapsulate the 8 heads concatenation. What comes out of that goes through a feed forward layer. And a feed forward layer is that example I gave you where we went from 512 to 2048, then 2048 back to 512 again. We just did that operation. So that's what happens there. And then these, remember, are just normalizations. We always do normalizations of the data. The tensor goes in, gets normalized, comes out. All right, so those are defined. Let's finish this one so that we can move on to the next one, which is multi-head attention, right? But we want to see what happens here. So notice, I'm using not the NN sequential approach, but the other approach that I like, right? I'm sure it has a name. I just don't know what it is. Something important is happening here, though. So if you look, X comes in. What is X? N by 40 by 512, correct? Okay. Normalization of the values. And then N by 40 by 512 goes into a head, a multi-head. That means that inside there will be 8 attentions, okay? But notice I'm doing a residual calculation also, which I've talked about, right? This gets rid of the vanishing gradients problem, which we've defined, and all those things. Because X is N by 40 by 512, and what comes out of SA is N by 40 by 512, we can do these things. See how that was genius, right? You know, creating that consistency allowed them to do so much more. All right, so they can do that. So that creates X over here, and then that X goes into a normalization, which goes into that feed forward. And remember, that's just going up to 2048, back to 512, and then another residual, and boom, we're done. Okay, that is just one block, but we created with NN sequential 6 blocks. So something goes in, comes out, and that works. Any questions about that, guys? Does that make sense? Any doubts? All right, perfect. So we're done with block. Now we move on to multi-head attention. Okay, so we move to multi-head attention, which should be this one. And this one should be somewhat familiar. It does have one new trick, programming trick. But this one should also be familiar. Look at the template format again. Class, name, which is unique. It inherits, and then module. We have our init function, and we have our forward function, okay, as usual. We do the super init. This one takes a number of heads, which is 8, and the head size, which is 64. That's the whole concatenation thing that we talked about. Notice here that we do another trick, just like the blocks trick a little bit. We create another list. This one does not need to be sequential. This one, in fact, needs to be parallel, right? The parallel heads. So we are going to say, this is a list, right? This list. which goes into this construct called NN module from PyTorch. It allows you to create this list for parallel processing. So notice that what we do is for drop the thing, so for underscore in range num heads. What is num heads? 8. So in this list, you instantiate what? 8 heads. Head, 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 head. The head is what will contain the attention mechanism. We're getting there. So now that I have this module list with 8 heads in it, it's basically, I've defined it, right? And I have it. So that's heads. Then I have a linear. This is just another one of those. I can go from 512 to 2048 and back, and this one just from 512 to 512. You always see these feed forward layers throughout. Dropout again, it's like a normalization maybe, but ignore it for now. We'll cover this later it's important, just not critical to this architecture discussion. And then, so now we are ready to do the forward, where we actually bring together the architecture. So I'm not using the NN sequential approach. I'm using the other approach, right? So what do? I take X, right? And notice this, how clever this is. I create a list. So for H in self heads. So what does that mean? Self heads is this one. That list of parallel heads that I have created, right? And I say for each one of those, so for each H in self heads, create a list of that head, and notice with an input that is X. So I'm essentially in parallel passing the tensor n by 40 by 512 into H, 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 and I do that in this list of 8 heads. But now every one of those gets its X, and the output of X, of H, of head, H will be what? N40 by 512. So N40 by 512, N40 by once it's processed. But this is how I create the heads in parallel. Okay, so that's what's been done here. And notice then, so usually X goes into linear, comes out to H1, goes into the next linear 2, becomes H2, and so on, right? We do the same here. It's just in a strange way. X comes in here in the forward, and it goes into each one of these in this for loop. H with its X, another H with its X, another H with its X, and they're going to be treated in parallel. Once the output is processed, if you look, they're going to be, the 8 tensors are going to be concatenated on the last dimension. That's torch cat. So this is what we did in the example where we concatenated the heads. This is exactly the same thing. The only thing is I kind of didn't use module list because I just instantiated the same head multiple times. All right, and now you get out. You see that? A tensor, N40 by 512. That goes into this projection, which, like I said, just maps it to 512 again. There's another dropout. We will discuss this later, and that's it. Do you guys see that? So that's done. Multi-head attention is done. You're out of that. But what is H, right? So we need to drill down, and this is the final class, which is one that you should understand really well because this is the attention mechanism. Okay, so if you look, a lot of it has been just getting to the attention mechanism. And then there is this feed forward. So let me, before I forget it, this was used also. So this feed forward was in here in the block. We had this FFW, which is this feed forward. So this is actually like the most common type of neural network. So if you look over here, what is it? Class feed forward, it inherits NN module. We have, once again, our init function and our forward function. We have our super init here, And notice that here's another example where I could have done this with the other approach. I totally could have. But, you see that? So they're interchangeable. So in this case, this is a perfect example. You use NN sequential. So you have an NN linear followed by a ReLU. And that's the other thing. You can have other things in there like ReLUs and softmax and whatever you want, But the idea is you don't have to put X that goes into H1 and all that like that. You just do it like this, and it's going to go in sequence. Now, the dimensions obviously need to be correct. Like everything still needs to be correct. These are just like programming abstractions. Okay? All right. So yeah, forward we will need. You can see all it does is in the second third of the semester, you guys will get tired because this will be like literally all we do. Just multiple data sets. But you can see it's an NN linear that goes from 512 to 4 times 512, and then from 4 times 512 back to 512. And there's going to be a ReLU, which remember, what does ReLU do? Given a tensor, it looks at all the values in there, and it transforms those values into, if they're negative, into 0, and if they're positive, it just lets them through. That's what it does. And there's a lot of these functions that we use in machine learning, as we will see later. Okay? Yeah, go ahead. So this one goes, so remember, all of this is always being applied to the last of the 3. So it's n by 40 by 512. So that 512 comes in here. That's what that means. That vector of 512 goes in here, and it's going to become 4 times 512, whatever that number is, if anyone knows. Why is yeah, why is it being done? Because you give it one more. So I'll give you guys an extra 30 minutes to work on the exam. Why? Do you see that? It's sort of the equivalent of that in neural networks. We make them deeper, we give them more neurons. It also it just came out of the attention layers, so it just made sense that you wanted to go through a more traditional studied neural network. Yeah. I mean that's a very theoretical question. I don't know exactly, but that's the traditional operation. Okay. And you could have done as many as you wanted, different dimensions. I mean, some people have written papers that are called ablation studies and of what actually is the critical thing in the original GPT transformer. And they have said, well, this is the important, and you can actually don't need this part, or this is essential, or something like that. I encourage you to find that paper and read it. No, I'm serious. They're interesting. But still, everybody still just uses this architecture, right? This is has been modified very little. All right. So anyway, so we've done forward. I think we're in good time. We're doing good time because we're almost ready to train, and that's really the key thing. All that's left is something that would have taken me hours to cover, but because we've already covered it, you guys should totally understand this in a few minutes. So I need to define the head class. And if you notice, that's the last one. All right. So let's take a look at this one. And you will see that it's pretty much the same thing we discussed before, just a few little variations, okay? So this is the head section. Notice, once again, class, a name, in this case, head. It inherits the NN module. It has the init function, right? And it followed by the forward function, right? That just like before. It's going to have all the familiar elements and a few normalizations here and there. All right, so what do we have? Head size, right? So we have 64. We initialize this one, right? The super init. This, you guys should know exactly what it is. in my example of attention, I would create a W and a B, and I do the matrix multiplication manually. Remember, linear does that for us, so we just really have to create for a function called key, query, and value. This is your KQV. And each one is an NN linear, and it's going to be of NN embedding to head size. Remember that these functions compress, right, from 512 to 64. Do you guys remember that? So that's why. So this is going to be 512, and this is going to be 64, which is a calculated value. And bias, notice I haven't even used it, but that could be true also. Got it? All right. So a lot of these things, if I make bias true, for instance, it might take longer to train. So these are like trade-offs you have to. All right. So once that's done, all of this should be super familiar to you guys. That's that whole trill discussion. So this is literally the same code. Trill def, torch trill. Remember, I created a torch of ones of size, block size, block size. So it's 40 by 40, right? And that's that thing. Remember, this was also there. I described it briefly. This doesn't have to do with architecture. It just has to do with telling the model. So when any tensor you create in the computational graph, when you do the optimization, it's going to try to update the values. But you don't want this to influence the update at all. So you just do this register buffer, and it becomes almost like a constant thing that is not used. Does that make sense? Because it's just a thing of ones. Okay? Do you guys see that? So trill def is being marked almost as a constant for PyTorch. Okay? All right. Drop out again. Ignore this for now. We will go into it, but just think of it as okay. Just think of it as it's still recording, right? Yeah, okay. I think my previous video maybe just finished. All right, anyway, so yeah, so we define these. So now let's look at the forward function, okay, where the actual attention happens. And after this, we are ready to start training. So X goes in, right? X goes in, and 40 by 512. It goes into the function key, which is K. So now this one is what? N by 40 by 64. Same for Q, right? N by 40 by 64, right? Is exactly what we discussed before of the attention mechanism. There is a normalization parameter, this 64 over here, which is this E2 here. Think of it as a normalization. If you look, all these are constant numbers, so you're just sort of dividing by that. But what is familiar to you is this, correct? So this way is Q times K. And the transpose we already discussed for the alignment. So when you do QK, it becomes that square matrix that is 40 by 40. We've already talked about it. So that's my way. And if you remember, this is the exact example I gave you. Then we applied to way the mask, right? Which was this self trill, which is this one over here. Torch trill, trill def. Yeah, I gave it the name trill here, so that's what it is. So self trill. Yeah, right. Sorry. So this register buffer gets the name trill, which is trill def, which is this one above. Okay. So then we apply trill to it, right? And we already discussed this logic where all the values were 0, we made it minus infinity. You guys remember we went over this so that when we run it through the softmax, right, it ignores those and it just makes the probability distribution over the actual ones. Yeah. Yes. The variable weights. Well, this is what I was saying, that we use NN linear instead. Yes, exactly. So usually you will always use NN linear. But I started by showing you what N linear is doing under the hood. So remember, in machine learning, there's a lot of encapsulation. So you create a whole bunch of lines of code, they get encapsulated into one thing that does everything for you. So I think we had discussed this a little bit before. So yeah, so in the past, I was doing, let's say it's K, right? So I would create WK, BK, and then I would do X, matrix multiplication, WK plus BK, and that would become actually K, right? And we did all of that. But you can also just do NN linear. So I can create, let's say, KF equal NN dot linear. I have to specify the dimensions, which are the dimensions that I would specify explicitly here for these things. You can, because NN linear is a class that includes all of this. So if you want to get those weights, let's say that you've already done NN linear, right? So now you have KF. If you want the weights, you could do WK. And if you, this should be this is a, and if you want the biases, do you understand? It's the same thing we're doing that, with the classes. Think of it as a class, right? It's got variables WK, BK, but it automatically creates them. And the forward function, so it's almost like if you wanted to create this whole thing, it's like class linear, right? And inherited module. So then there's a WK in there, there's a BK over there, and this is in the init. And then in the forward, there's a what? There's a y equal, oh, and then there's an x that comes in here. So there's an x wk plus b. It's all happening inside. So instead of creating everything, you just instantiate that class, but it's essentially the same thing. Yeah, you can, yeah, just, yeah. What do you mean automatically updates the weights? Weights are updated when they're trained, when you train. Align, I mean, you create the architecture so that data goes forward, a prediction comes out that's compared to the real value. Those two are compared somehow via, cross entropy or something like that. And that information via another algorithm called stochastic gradient descent makes its way back. And that information is what is used to update the weights of everything. We'll see. Yeah, I mean, we'll have some abstraction, but we will have a function where we do the training. Yes, we still need to see that. So maybe if you wait for that part and then, but yes, actually, we spend more time building architecture than actually defining training things. That's actually why we need torch. So that's just to give you an example. Everything we've done so far, we could do in NumPy. But what we can't do in NumPy is that whole differentiation that happens, that whole process of updating the weights. That's a torch or TensorFlow thing. It's why they exist. Okay? But anyway, so let's go back. We are almost finished. So let's go back to, oops. What did I do? Okay, let's go back to the code. So we have a head. I think we were here. Yeah, we were here. So if you remember, we just did KQ, K matrix multiplication Q. So we have 40 by 40. Our mask is also 40 by 40. So then to weigh, which is the attentions, we apply the mask. Wherever the value is 0, we assign minus infinity. We discussed this in the previous lectures, videos. Go back to that for that explanation. And now weigh just is run through a softmax, as you can see here. And that will do those probability distributions that add up to 1, right? We discussed that as well. And then weigh is run through yet another dropout. We will discuss dropouts later. And finally, you remember that X also runs through a value function to create our V. And then finally, we just do weigh matrix multiplication V, which gives us what? N by 40 by 64. Remember that this is just one of 8 heads. In parallel, so N by 40 by 64 comes out, we concatenate them, we have N by 40 by 512. Hey, we're done. That's it. That's the GPT, and that's Chat GPT and Llama and DeepSeek and all of them. And after that, yeah, sure, this is like 90% of them. They have other few things here and there, but essentially this is what's going on. All right, so now maybe moving into training, right? So all these architectures, I believe, are done. So we've done all of this. So we need to run this code all the way to here. So let me do that. So it's head. I'm gonna run it. And I think actually I saw that the GPU had, I'm gonna run all of this all at once, guys, because I saw that the runtime failed on me. So I'm gonna switch to a GPU. So because I'm training a GPT, I just want to be a little bit faster. So I'm picking my GPU here. I'm going to save it. Okay, it like restarts everything. So I have to run everything again. So I'm running the libraries. Okay, that completed. I'm running the parameters. That completed. Reading in the data from the drive. So you can see I got the same number of tokens. Those are my letters. There's the chars have been updated. Vocab size. I have 88. I create the tokenizer, show that it works. Back. I tokenize the entire book, The Adventures of Huckleberry Finn, split it into train and test. We discussed get batch, so that has been discussed at length. Did some examples that are not really needed, just to further illustrate how it works. This function we can discuss later is just like a metric. And then here head should work. Okay, perfect. So head loads. Good. We also define feed forward. We define multi-head attention. We define block and the GPT model. And this one had everything, the generate function. I'm only training today, so I will discuss this in the next class, but we're essentially done. So now that this is all instantiated, we proceed with training. So this is like, you can think of machine learning as being two things. So we've finished one thing. And then there's the other thing. So we finished the architecture part. Now we have the training part. Stochastic gradient descent. Geoffrey Hinton, if you've ever heard of him, right? Won a Nobel Prize in physics for this invention that makes this possible, right? So that's going to be the second third of the semester will be that. So let's proceed. I want to see this start training, okay? And then I'll describe it because it does take a little bit. So what do? I instantiate GPT model, this class. And of course, When I instantiate this class, that class will instantiate all the other ones. Now I have my model. Model is usually the term you use, the word is common. Everything, whether it's very simple or whatever, you just call it model. We load it to the device. Currently, I'm using a GPU, so it's probably loading to that GPU. I'm calling it M. And then now I'm introducing the other part, the second part of the code, which allows us to do training of models, another machine, if you will, called an optimizer. So in this case, from Torch Optim, we invoke Atom. Sometimes this can also say SGD. Regardless of what it says, they're all based on the same thing, stochastic gradient descent. There's only one thing, believe it or not, there's only one mechanism to train all AI that is neural network based, and it's stochastic gradient descent. The paper that Geoffrey Hinton wrote with his colleagues in 1984 that actually proved this possible, and that earned him a Nobel Prize. It's right here. Okay. There's quite a bit that goes into this. I cover this in 365. We go from the perceptron all the way to here, but in this course, I don't cover that. All right. So anyway, so here we have, I'm using Atom. Atom is just an improved, it's got improved efficiencies in stochastic gradient descent. It's faster, better for some reason. Now notice the parameters that it takes are two very interesting ones. It takes the learning rate, which you've already discussed. That's by how much you update, whether by adding, right, at plus or minus. And then notice over here what I'm doing. I'm mapping from M, which is my GPT, all that massive architecture that I just created. I'm mapping that to this optimizer by saying M dot parameters. This is how I connect the two. This is the optimizer. This is the GPT. They're now connected. So this one knows that it's this one that it's processing and so on. That M parameters is all the weights and biases that you've seen in this architecture. Every time I did a NN linear, WQ, a W and a bias. NN linear, W and a bias, right? So all of those weights and biases are this. So this is when they say Mistral 64 billion. 64 billion of these weights and biases. Or I think ChatGPT is like 1 trillion. Yeah, go ahead.
So it's like all W sub every time. So like the first time we ran linear, that was W sub one, wait, or E sub one. Then when we ran it again, now it's W sub two, E sub. Run linear a lot. It raised up this 4 billion.
Yes.
Okay.
Exactly. Just think when we and I did 6 blocks and 8 attention heads, and all of those had, so that's all of them get created. Thankfully, we don't have to index them ourselves, right? Because that would be horrible. Do you see that TensorFlow 1? You almost had to do that. So that's why it went away, but it was great. I love TensorFlow 1. Anyway. All right. So anyway, we're done, right? So we did this. We instantiate the GPT, tie it to the GPU, create the optimizer, tie the weights of the model to the optimizer, and tell it the learning rate. There's more parameters. We'll see them later. And now, finally, after all this time, right, we get to train. So let me just run it, leave it training, and then I'll start describing. But now this is the moment. Currently, the GPT has random weights, but now I'm going to start grabbing chunks from Huck Finn and train it. So I'm going to run it. And let's take a look for a second there. And it's going to take a while to train, not very long, because I'm using a GPU, right? And it's only Huck Finn. There it is. So there's the first iteration at step 0, and the train loss is 4.68. You can ignore val loss at this point. That's not something so important for now. But note, this is what you care about. So for now, there's the whole math of how this works. We will discuss this later. But for now, the important thing is what? That you want this loss value to go down. Okay? That's the key. If you see this nicely go down, great. That means the model is probably learning. Okay, but that's essentially the idea. All right, so let's leave it training for a while. As you can see, it's processing. In a second, we'll see, I think, SEP 500, and hopefully this loss will go down. But let's focus on this one over here and see how this works, right? So this is how you train your models in batches. Remember, it doesn't make sense because you wouldn't have enough RAM memory to give it 1 trillion books all at once. You can't, in fact. What you do is you give it 10, 20 books at once. I don't know, right? But something like that. So we now notice, and we're going to repeat this a number of times. But essentially, the way that we pick the data is based on how we define the function get batches. And if you remember, get batches just looks at whatever the text is and randomly picks some indices, slices out a chunk. That chunk is shifted by 1, and that's your X and Y. Do you remember that? So that's what we do. And we do it in batches, not individually. So I think iterations was like 6,000. Play with that parameter, more or less. But you're going to have limits, right? The more data you have, the fewer GPUs you have, the fewer iterations you can do. That's just the downside. It's the world we live in. This is the era of AI. It's called big data. And you really, if you have fewer GPUs, you are at a bit of a disadvantage. So you do this. No, this part over here we can literally ignore for now because it's just printing losses. So it's this value that's being printed. So you just it's just showing the performance, but it's not so critical to understand. Let's focus on this logic first. These 5 lines of code are doing all the heavy lifting. Okay, so notice we do. Get batch is tied to data, and data came from Huck Finn, the book, right? So we do every iteration. Let's say we're doing 6,000 iterations. So at iteration 1, we grab a batch of data randomly. XB, YB. Do you guys see that? So that's those 2 tensors shifted by 1. So we got the real data for input and the real data for output that we will use to train. So then we do M, the model, right, which takes in XB and YB. Why does it take YB? Because we do the loss inside, right? Another way that we could have done this, which is actually a way that we're going to see this later, is we could have done logits equal M, comma, just XB. Do you see that? No YB. And then we would have used this here. But here, so loss would have been equal to F cross entropy. This logits here. Oh, sorry. This should go underneath. Sorry. Like this. So this logits here would go in here, right? Logits. And then this is not targets. What would this be? YB. Do you see? Because it gives you XB and YB. So X goes in as input into the model to produce logits. That's another way of, if that's confusing, say YPred. I like to use YPred. And then YPred. You see what I'm saying, guys? That's essentially what's happening. Is just that cross entropy is inside the class. It's inside here. In this segment. It could be in there or outside. It doesn't matter. Any questions on that? All right, so So essentially here then, um, XB goes in, Y pred, then the cross entropy Y pred is compared to YB. That produces this thing called loss, right? And then that's where we are here. So notice that M returns loss as well, right? So I'm going to delete these two to go back to the original code, but I did that just to show you what was happening inside the function. Okay, any questions on that? All right, makes sense. So then we can see, okay, we grab a batch of XB and YB. We provide the XB for the model to predict that, and also we provide the actual real data. So then the predicted is compared to the YB, and then it just returns the predicted, and it returns the loss itself. This is important because that loss is the difference between the predicted and the real. So think of it this way. If at the beginning it's really bad, right, at predicting. So when it predicts something, we have the cat is sleeping, but it's going to predict A, B, 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 C, C, C. That's really bad. So that comparison is going to give a loss that might be really high, like 4.68. Do you see that? But once it does, the cat is sleeping on the chair, and it says the dog is sleeping on the chair. Okay, it's not as bad. So maybe the loss goes down to 1.28. Once it gets the cat is sleeping on the chair and the cat is sleeping on the chair, then that loss is zero. You've essentially minimized it to the point of zero. It'll never be zero exactly because the batches have different sentences anyway, so you will never get perfection, but that's the idea. So the key is that loss is really important, that connection, right? And that's where the computational graph comes in here. So you have these three, after you've calculated the loss, you have these three lines of code that will be in every single PyTorch script you ever write when you're doing the optimization. So it nicely does not change. So the first one, optimizer.zeroGrad, is more of a quirk of PyTorch. PyTorch accumulates these values, and you have to zero out. You can see that zero grad, so you have to zero them out every time. Otherwise, it would accumulate. So you just have to keep that in there. But really, these two are the ones that relate to the algorithm itself. So in the first one, loss backward, essentially, it takes the neural network exactly as it is with the calculation, loss backward, and it'll calculate the derivatives. It's essentially at that moment in time, it'll calculate those plus and minuses. Do you remember that I talked about? Do we have in the update, do we have a plus or a minus? That's what loss backward does. How it does that, we got to talk about that because that's some serious math that accessible totally, but it's something that we need to talk about. How stochastic gradient descent actually does what it does, all right? So we'll do that later. But just keep in mind at this point, it does, it takes the computational graph, calculates whether for each one you're going to add or subtract. Then after that, optimizer step literally takes whatever you selected plus or minus and does the operation with the learning rate. So it updates at that moment in time. Do you guys see that? All right, so we will discuss the algorithm later. It's still processing. So I want to say one more thing, all right? So, and then we'll pretty much wrap up. So, which is related to this topic. So all we have been doing, oh yeah, go ahead. Are you using CPU or GPU? That's an important one. Yeah, okay. So this is just, an important thing. You never actually code like this or anything, but this is what's happening behind the scenes. So TensorFlow is called, which is the Google variant, is a flow of tensors. Okay, that's what that means. PyTorch is also a flow of tensors, just with a different name. In the whole memory scope of PyTorch, of these frameworks, you're creating a computational graph. You guys have done like in data structures, right? Graph, breadth first search and all that stuff. It's kind of like that, okay? So you create a computational graph made up of tensors and operations, okay? I'll keep this super simple. We have an X tensor, and when we have a W tensor, right? That's just data. And then we have a matmul. That's an operation. The product of that is something, let's call it T1. And what do you do to that? You add a bias. All of this, you guys, whenever you're doing, and in linear, you're doing this, okay? And then that moves on to become, let's say, H1. What is H1? Yet another tensor. What do you do to H1? W1, let's say, matmul, very good, matmul. And that produces, let's say, T2. And then you tie it to B2, let's say, and that produces, and let me just do this. And that produces H2, correct? But let's actually say that that creates Y, because, I'm going to run out of time if I keep doing it. So Y hat in particular. What is Y hat? Another tensor. Do you guys agree? So then what did we also have when we had X? We had the actual Y, and that actual Y was also a tensor. And we applied to it an operation. In this case, what is that called? Cross entropy. Don't worry, we will discuss cross entropy, I promise. So it's based on entropy information theory, right? Claude Shannon. So what's going to happen with this? It's like matmul, but a different one. Oh, yes. Very good. One of them should be Y without the head. You're right. That's the real data. Yeah. All right. And what happens when we do this? That results in loss. Do you guys see that? My computational graph, that variable loss, it's literally this. And it's linked to cross entropy, which links the real to the predicted. And the predicted is linked to this whole architecture back to the X. This is very real in what is happening behind the scenes. So when we do this training, what happens in that back prop, right? What was it called? It was called backward. So loss backward. At this point in time, this is like a giant function, right? So when it does loss backward, that step, it's going to calculate all these differentiations, which is something we need to define what that means. But essentially, it's like it's going to look at the data, right? Imagine that this data represents a graph like this, right? For some reason, don't even worry about this too much, but it just represents, this represents this graph. So it's going to say, and this line here is represented by this function, which is made up of all these parts over here. So I have here a W, let's call it WA. And WA is that, tied to something like an error that you're measuring. And then I have another WB, and that WB is actually this one. Do you see that? So this is what's going to happen. And again, don't worry so much, but when we do this backward, this whole thing, computational graph, actually takes a relationship between error and the weights. Okay, we will see this later. So what this can be represented mathematically, and then we can apply calculus to it. the derivative in particular. And when we apply the derivative, what the derivative tells you is the slope of the point and where this point is on the curve. For this one, we would know something like that. If we were a WC, another weight, we would be on this side, so then it would look like that. So this is calculus. Like calculus does this. You take a function, take the derivative of it with respect to a variable, it tells you this. Again, we'll cover this. I'm just kind of tying this sort of to here, and then later we'll spend a lot of time on it. So what's the value of this? It tells you if it's sloping in that direction or in this direction. Do you see that? So that's the equivalent of, okay, if it's sloping in this direction, I need to add. If it's sloping in this direction, guess what? Minus, because I need to go in that direction to arrive at the point that is at the bottom. There will come a moment where this value is like this. At this point, it's neither positive or negative, it's 0. And so you would know theoretically that you arrive at the bottom. Therefore, that W must be the best one. But that rarely ever happens because that's more theoretical. So it'll get close without ever reaching that. And this is a super simplified example just to kind of give you a lot of the moving parts. We will discuss this a little, later when we talk about stochastic gradient descent. What's important for you to understand is that backward takes the computational graph like a snapshot in time, and it just calculates the pluses and the minuses. And then the other term, optimizer step, says, okay, for every single variable, I know that sign now. It's a positive or a negative. And then I know the learning rate is 0.03. So boom, I update all the weights, layer by layer. Okay? So that's the algorithm. To understand that, we have to use a much simpler example. But that's essentially what these two. So that's what I'm saying is like so much is happening just by doing these two commands. Yeah. And that's why we need Torch or TensorFlow, because they do like amazing things behind the scenes. Okay. So, but yeah, so we'll cover this later in the semester. All right, great. So I think actually we are done. We have 5 minutes left. So I think we should be able, I hope it finished training already. Let's take a look. Yeah, finished, right? So you can see, what do we see? So we have the green check. All right, it did about 60,000 iterations. And if we look at the loss, it nicely went down. So from usually the first is the first like few iterations you see the maximum like improvement. So you can see here it went from 4.6 to 1.6. Then it stabilizes, but it went down all the way to 1.10. Do you guys see that? This is what you want. You want that loss to go down consistently like this. Transformers are very good at that, actually. When we do other things, they're always they're not as great. Sometimes they go up, they go down, but this one is nicely. So now let's go ahead and just ask it some questions. So we can do that by doing the following. So if you notice, you have to always give it something. So you have, not even but like you have to give it a special character called start of sentence or something, just something so for it to start. So here I'm giving it the first index. So you can see I give it this tensor that goes in. It goes into mgenerate. If you remember, this is the one thing I didn't cover today. Just keep in mind, mgenerate just calls forward. But we will cover this on the day of the exam. And you tell it that you want 500 tokens. Do you see that? So in this case, 500 letters. And then once the text is generated, Why do we use this function called decode? Because it's integers and we need to convert it to the letters. Do you guys see that? All right, let's go ahead and proceed. There it is. So, is it ChatGPT? No. Can it reason? No. But it was only trained on Huckleberry Finn. It does get the, there. That's like big, right? Especially because it's just using letters. It actually mentioned Tom Sawyer here. Think about it. It's reconstructing that from us from letter by letter by letter, and yet it is at least sounding like the adventures of Huckleberry Finn. So that is something. What now your question, what if I had used tick token instead of this? Well, that's what you guys are going to find out when you do your homework assignment. So now let's take a look. I'm going to do another one, just a couple of examples. So it's processing again. It takes inference. Inference is expensive. I don't know if you guys know, but this is like OpenAI loses money actually, especially for people that reason a lot, the models for very complex problems. They are actually probably losing money because inference, this is running on the GPU and that's GPU time that they have to pay to Microsoft Azure or AWS. Oracle now is the big player. All right, and then I think this is the last one. I'm going to create an actual question, and we'll wrap up with this. So where is Huck, right? So first I start with the string. I encode it as a list of integers. You can see it here, so I don't have to print it. Those are the integers. Then I'm going to convert it into a tensor that is on the GPU and all that stuff. Okay. What's here? New NP. Did I miss a variable? Yeah, I guess I missed this one. I have to convert where is Huck? Yep, there we are. Okay, so now this is converted into a tensor. And there you are. So it's processing whereas Huck through the transformer, and it's not training anymore. It's just doing inferences, using the train weights to produce values. And if you look, that's its answer. So whenever you talk to ChatGPT, this is what you're doing. There is no concept of question and answer. There is just the string that you give it and then the string that it generates after that. So if you notice, it actually returned the question to me because it only predicted what. And then that became the input, maybe popped off where, and it predicted makes. Do you guys see that? And then you use that and maybe popped off is, and it predicted you and so on until it, and I told it to predict 500. See, if I change this to, well, let's make it shorter because take longer. Again, it's not, it didn't save something in memory and reuses it. It has to regenerate it again because it always goes through the model. Do you see that? And it created a shorter sentence. Yeah. See, this is a good thing because there's this randomness. So it's not necessarily always going to be the same thing. Yeah. Yeah, but it's not the, yeah, it's, where is fucking then? Yeah. They do come out random. So if I have seen models, especially image generation, where if you don't give him anything, they always generate the same image, but you don't give him anything. So like but we did that, right? I generated nothing essentially. Archie got two. Oh, rope, oh, bum, they're not the same. So it's made to generate different. If you give it an actual question, then it'll tie it to that because, if I especially give it a longer sentence, right, it'll try to address that. So I know that it does this. Why does it do it in the architecture? Well, first of all, there's a lot of ways it could go, maybe. Because it is the same. I'll have to look into that, to be honest. I can't think off the top of my head right now where in the architecture it's doing that. Um, I would just say right now there's so much going on that it can go in this direction, that direction. But yeah, I'll look into that. It's a good question. All right, guys. So we're only 4 minutes past, right? And we've covered the entire GPT. I only didn't cover the gen function. So this one because that's a different kind of thing. So we'll cover that next class, but we are essentially done with LLMs, okay? I should say we will continue to talk about them throughout the semester as a motivation. You guys are doing your homework, but we have to now drill down into other things like stochastic gradient descent. We also have to focus on not text, but like regression problems. And so there we will build up a sequence from very simple regressions to multi-layer perceptrons, deep neural nets. And so that stuff, because it's easier, allows us to talk about the more in-depth topics like cross entropy and things like that. And whenever I can, I will tie it back to GPTs. All right. Okay, so let's stop here.